Good morning. Good morning and welcome to the class. Hello. Good morning. So, good morning. Everybody, welcome to lesson 19. Introduction to Organic Chemistry and naming hydrocarbons. The other word for naming in science is nomenclature. Nomenclature. That's a new word. So today, intro to organic chemistry and naming chemicals. So organic chemistry, what is it? It is the study of structure, properties, composition, reaction, and preparation of carbon-based compounds. And the big parent of the organic molecules are the hydrocarbon. They have carbon and hydrogen. So all organic compounds, all carbon-containing compounds, with exception of oxides and carbides, they are, for example, calcium carbide, this is this, and carbonate, they have this. So carbonic acid, carbonate, they are considered inorganic. So oxide, carbon oxide, carbon dioxide, carbon monoxide, carbides that have C2 connected to, for example, calcium, and carbonate, these are containing carbon but are considered inorganic. All the other carbon-containing molecules, especially those that have CH, are considered organic. That is the difference. Is that clear? Okay, goody. Then we continue. So what does the word allotrope means? Okay, it is one or more form of a chemical element that occur in the same physical state. So, for example, what does that mean? Graphite is solid, diamond is solid, and fullerenes are solid, but they have different forms. Okay? And the different forms are there because the atoms are connected in a different way. So, for example, here we have this carbon connected to 3 others. In diamond, it is more complex. Here, the connection is also different. So, when you look at diamond and graphite, they look completely different, don't they? One will cost you a fortune, and the other one you have in your pencil. So, these allotropes, or allotropes, depends how you want to pronounce it, they have different chemical and physical properties. Graphite and diamonds are typical example. They're both all carbon. This is just carbon and this is just carbon, but graphite is soft and diamond is extremely hard. And the shape, the colors and the shining is also completely different. Graphite is dull and diamond is beautiful. Okay, so you can change from one allotrope to the other in response to different pressure, different temperature, and exposure to light. So you can take graphite and convert it to diamond if you put it under enormous pressure and temperature. Then you will get synthetic diamond. And this is what happens in nature also. You have this graphite and they're pressed due to the fact that tectonic actions pulled this graphite downwards, and it comes under enormous pressure and temperature down on in under the Earth's surface, and it turns to diamond. Okay, so let's continue. So when you look at organic compounds, we have those that we're going to talk about a lot. Will be the carbohydrates, the sugars, the fats, the lipids, the proteins, the RNA and DNA, the nucleic acids, and we will talk a lot about ATP. So before we reach the stage that we can discuss carbohydrate and lipids and proteins from the chemical point of view, we need to cover some more ground before we get to these beautiful organic molecules. Okay, so organic chemistry. Organic chemistry is, again, the study of carbon compounds. So why did nature select carbon to make the most important molecules in the body, and not only in our body, in dogs and cats and whatever? Why carbon? And here's the reason. Carbon atoms form very strong covalent bonds to each other. So C-C bond, very strong. Okay. Also, carbon-carbon bond can be single, can be double, can be triple, which increases the variety. And that is also what you want in nature, to have big variety. And also, the carbon atoms, when they are attached together, they can form straight chains and branched chains and rings. So not all atoms can do all these. That's why carbon. So look at that. This is a straight chain. These carbons connected to each other in a straight chain. This is branched chain, and the ring is a closed system. So the carbons are connected in something that you can envision a circle. It's of course not a circle, but that's how you can. This is the metaphor. So you can have a closed construction with 6 carbons, but you can also have with 5 carbons, and you can have with 4 carbons, and you can have with 7 carbons. And not only that, you can have a straight chain, you can have a branch chain, you can have a ring, and you can also have a combination of all. So, for example, okay, you can have this is a ring, this is a branching, this is a branched chain, this is another branched chain. All these are possible together. So the fact that you have a ring, it doesn't mean that you can only have a ring. Or if you have a straight chain, it doesn't mean that you only have a straight chain. You can have a combination of everything. And that increase, of course, increases the diversity. So when we talk about organic compounds, we talk about hydrocarbons, okay? And hydrocarbons are divided to two subcategories, aliphatic and aromatic. And the aliphatic are further divided to subcategories, alkan, alkane, alkene. And these compounds have only carbon and hydrogen. But you can have hydrocarbon derivatives. Hydrocarbon derivatives can be a molecule that has carbon, hydrogen, and oxygen, or carbon, hydrogen, and nitrogen, or carbon, hydrogen, and a halogen, Br, Cl, I. So those compounds that have, in addition to the C and the H, another atom, we call those hydrocarbon derivatives. Are there so far any questions? No. And just for your information, when this course is over, you will know what alkyl halide is, what alcohol is, what ether, aldehyde, ketone, carboxylic acid, amides, imines, amines, all this you will know. But one step at a time. Okay, so we have several types of formula in organic chemistry. Okay, we have a general formula. I think you remember it from lessons before. It tells you that any member in a series. So, for example, when I have C2, let's just take a piece of paper. CnH2n plus 2 represent a whole class. Okay, because when n is 1, n is always a full number, a whole number, and a whole positive number. C1, then H would be 2 times 1, it is 2, 2 plus 2 is 4. So CH4. This is one member. When n is 2, C2, H, 2 times 2 is 4, plus 2 is 6. This is another member of the family. When n is 3, we have C3, H, 8. So you see, this formula represents all of these guys because they all have this composition of C and H2n plus 2. Is that clear? Perfect. Perfect. Okay, so general formula. And then we have the molecular formula that is telling you the exact number of atoms of each element in the molecule. Like here, 4 carbons, 10 hydrogens. Okay, so it is a member of this family because if you take n is 4, we have C4, H, 2 times 4 is 8, plus 2 is 10. So this represents everybody. This represents a situation where you have 4 carbons, 10 hydrogens. Why didn't I say one molecule? Why didn't I say one member? The answer, of course, is under. It is exactly like that. It is because C4, H10 does not represent one molecule. This is C4, H10, and this is also C4H10. So only when you have the structural formula, you have the real structure of the molecule. And let's look. All right, I remove the garbage. C4H10. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is C4H10. But also this. This is straight chain, this is a branch chain. These are two different molecules. Different boiling point, different melting point, different everything. So C4H10 does not represent one molecule. It represents more than one. How do you know which one to write? Yeah, that's the whole thing about the course now. So that is coming soon. Okay, so we have the general formula, we have the molecular formula, and we have the structural formula. Now, a little bit story about the carbon. Okay, carbon, if you look at methane, the bonds to each hydrogen, so this bond and this bond and this bond and this bond, they are the same. But this doesn't make sense. This doesn't make sense. If you look at the electron configuration of carbon, carbon is atomic number. Which atomic number is carbon, ladies and gentlemen? Which is the atomic number of carbon? Well done, Joshua. Dastan. You should be able to discriminate between atomic number and atomic mass. So 6. 1s2, 2s2, 2p2. Okay, do you understand the difference between atomic number and atomic mass, Dastan? Yeah, don't be too fast, because too fast, you don't think properly, you make this kind of mistakes, okay? So 2, 2, 2. So we have the valence shell. The valence electrons are 4. All righty, so we have the 2s2 and 2p2. Now, if you look, carbon is missing 4 in order to become a noble gas. So 1 here, 1 here, 1 here, and 1 here. It means that these two will be a different kind of bond, because we have 1 electron coming from the carbon, and also here 1 electron coming from the carbon, and another electron coming from somebody else. The green ones are coming from somebody else. And this bonds, or this bond, will come from, will be completely different, because 2 of the electrons come from somebody else, not from carbon. So there could not be that carbon has 4 identical bonding, because the first 2 will be identical, these. Okay, this will be identical if the additional electron comes from hydrogen. Okay, and this would be different. So how is it still possible that all 4 bonds are the same in methane? Okay, how is that possible? And the answer is hybridization. Hybridization. What does it mean? It means mixing orbitals. So carbon does not have, when he's going to bond, he's not having pure s and pure p orbitals when he's forming bonds. It's hybrid orbitals. What does that mean? Let's leave this for a second and look what carbon is doing, okay? Carbon is doing like this. This is the electron configuration of normal carbon. 1s2, 2s2, 2p2. What carbon is doing is saying like this. This will be a lone pair. That will be miserable. This is empty. What I can do is I can do like this. I can take these electrons, okay, and I would create 4 new orbitals. So I will take these 2 electrons, I will take these 2 electrons, and I will create 4 new orbitals. Okay, where these orbitals will be. Okay, if you create 4 new orbitals, look what happens. The 4 new orbitals are lower in energy than the p orbitals and a bit higher than the s. So it will be somewhere here. Okay, it will be somewhere here. So a bit higher than the S, a bit lower than the P. And what is the point? What is the point? The point is that now also these electrons are bonding electrons. Before they were non-bonding because this orbital was full. Can you see that? The 2 S's is in a single carbon, it is full. And the 2p is not full. So what is he doing? He is taking these 2 electrons, creating new orbitals, taking these 2 down in energy, this up in energy, and in total, look, the list of, or the series of these orbitals that are created new is half full. Half full is stable, is good. If you don't remember it, you should go back to the electron configuration. Does this ring a bell? Yes. So now not only that, but now all electrons become bonding electrons and are able to enjoy the calming and the attractive properties of 2 nuclei, the carbon and the other entity that is bonding to the carbon. So when it suits him, carbon can create 4 new orbitals, and we call such orbitals hybrid orbitals. They are a mixture of the s and the p, and since we have 1 s orbital mixing with the 3 p's, this one, and this one, we call this sp3 hybridization. Okay, so far so good. Why? because we have one s orbital mixing with 3 of the p's, px, py, pz, sp3. When it suits him, carbon can also say like this, you know what? I only need 2 of the p orbitals. So what he does, he creates 3 new orbitals that are lower in energy than the p and a bit higher than the s. And you see now I have only 3 that are low and 1 that is high. This one is not mixed. It is the same energy content as the non-mixed p orbitals because it is not mixed with the s. So carbon is able to select and say, I don't want all the p's, I want only 2. And then he creates an sp2. These are 3 orbitals that are a mixture of 2 of the p and 1 s. And the leftover p is not mixed. It is pure p. It still can form a bond, but it is not the same type of bond as the brothers here. It's higher in energy. And carbon can also say, okay, well, I don't want all 3p orbitals. I want only 1. So fair enough. Here we have 1 of the p orbitals mixed and 2 left over. So 2p left untouched. You see they're the same energy level as the untouched p because they are untouched. So carbon took only 1 of the p's and mixy created new orbitals, new hybrid orbitals, and this is called sp1 or sp. So carbon can take all 3 p's, 2 or 1. The way he selects, and of course he doesn't have a brain, he doesn't think, it depends to which atom he's binding. And we're going to see what is sp3, what is sp2 bond, and what is sp. Okay, so carbon can choose who he mixes. If he mixes 1s with all the p's, we have sp3. Okay, marked here. sp3 is 4 new orbitals. 1, 2, 3, 4. These are all hybrid, all mixture. When we have sp2, we have 3 new orbitals. 1, 2, 3, and 1 of the p's not hybridized. It can also take only 1 of the p's, and then we have 2 sp orbitals, and we have 2 p's not touched. Are there any questions so far? So carbon, look at the situation and adapt quickly. Okay? Here we have carbon, as you see it in the periodic table, single atom. When carbon undergoes bonding, it can either take all the p's, or 2 of the p's, or 1 of the p. When all the p's are involved, we have 4 new orbitals They are called the sp3 orbitals. So 4 sp3 orbitals. When one is left over, I have 3 new orbitals, and they are called the sp2. When only one of the p's is used, I have the sp, 2 new orbitals, 2 hybrid orbitals. And that is also what you have here. 1 s orbital and 3 p orbitals form 4 sp3 hybrids. 1 s with 2 p's, 3 sp2 hybrids. 1 s, 1 p, 2 new hybrid orbitals that are called the sp. Questions? No. Okay, all right. So when we look at molecules that have sp3, when we have sp3, carbon has 4 partners. When we have sp2, carbon has a double bond, 3 partners. When we have sp, we have triple bond. So we can look very clearly and see the molecule and see whether it has all single bonds. That means 4 partners to the carbon. We see whether it has a double bond, and we see whether it has a triple bond. If it has a triple bond, if carbon has a triple bond, it created a triple bond. It is an sp hybridization. A double bond is sp2 hybridization. And carbon-carbon single bond, when the carbon has 4 new partners, like methane, for example, or in ethane. This is sp3. This is sp3 hybridized carbon. This is also sp3 hybridized carbon. Let's look at what we have to make sure that we understand. Carbon single, carbon single. This is a double bond. This carbon is sp2, and this carbon is sp2. These 2 carbons underwent sp2 hybridization to enable the formation of the double bond. So let's call this carbon A and carbon B. Carbon A and B undergo sp2 to make a double bond. Okay? These 2 are sp3 and sp3. Why? Because they have 4 partners. Look at this carbon. This is partner number 1. This is partner number 2. This is partner number 3. And this is partner number 4. Look at this carbon. Partner number 1, partner number 2, number 3, number 4. sp3. Okay, let's look at triple bond now. sp. This carbon, 2 partners. hydrogen, and this one. So this is an sp carbon. This guy here is also an sp carbon. Why? Because it has this partner and this partner. Two partners. sp. So carbon A and B did the sp hybridization to facilitate the formation of a triple bond and another bond to hydrogen. Okay, all right. So when I have the sp3 hybridization, sp3 hybridization, carbon is going to be tetrahedral. If you wonder what a tetrahedral is, this is this. We should recognize it because we learned about it in week 2. The sp2 trigonal planar and the sp linear. So this carbon that has triple bond, that section is going to be linear. Okay? Double bond, that section is going to be trigonal planar. And carbon that is having 4 partners, sp3, will be tetrahedral. Bond angle of tetrahedral, 109.5. Bond angle of trigonal planar, 120. 180 to linear. This is something that we need to bear in mind. Are there any questions? Okay, you see here, sp3 carbon, 4 partners. Partner number 1, number 2, number 3, number 4. sp3, this carbon is tetrahedral. This is also sp3, 4 partners. 1, 2, 3, 4. This is sp3. Also, this guy here is sp3 carbon, tetrahedral. Double bond, 3 partners. Partner number 1, number 2, number 3. I'm talking about the carbon marked in green. 3 partners, sp2. We have a double bond. When we have a double bond, sp2. Also, this guy here is also sp2 because both are forming the double bond. sp triple bond. So this carbon is sp hybridized, this one too. Okay, all right. So look at this molecule here. This molecule here has sp3 carbons, sp2 carbons, and sp carbons. Make sense? All right. And also here, you see sp3, sp3, sp2, sp2, and what you see also, that also oxygen can form hybridization, okay? Also nitrogen can do that. Okay, so we don't talk about the oxygen and the nitrogen. You're not a chemist. Now, only the carbon. Capiche? All right, great. Multiple bonds, multiple bonds. Okay, now back to the hybridization, back to hybridization. Let's take a piece of paper. Carbon, 1s2, 2s2, 2p2. 1s2, that is not a valence bond, a valence set of electrons, we usually don't even look at them. We look only at the valence electrons because they are the ones that are responsible for the movement and for the chemical bonding. So this is 2s2 and this is 2p2 electrons. All right. When I have sp2 hybridization, let's remove this. We're not going to talk about the kernel electrons, okay? We only talk about the valence because those electrons are moving. So far, so good. So let's see what we have. When we have sp2, carbon took 2 of the p orbitals. Okay, 2 of the p orbitals. 2 of the p orbitals. He left 1 untouched. So far, so good? Okay. Remember this because now I'm going to draw it again. Okay. 2, 3, plop, 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 and this one. This is the untouched, not hybridized, and these are the hybridized. Okay, these are part of hybridization. So you clearly see that this carbon that has an sp2 will have 3 same or similar bonds and 1 different. This is high in energy, these are low. So they will be, the carbons will have 4 arms like it always has, but 3 of the arms will be the same and 1 will be different. Is this clear? So we know that the sp2 is when I have a double bond. Okay, so what is going on? Let's look at how a double bond is made of. Carbon, carbon, hydrogen, 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 hydrogen. Okay? The bonds that come from hybridization are called sigma bonds. Capiche? But I have 1 electron that is unhybridized and is also able to undergo bonding. This is what makes a double bond. This electron is creating a pi bond, a bond between 2 carbons. Okay, it can be with other atoms, oxygen and nitrogen, but we're not talking about them right now. The second layer of the double bond is coming from this unhybridized electron, and it is called a pi bond. So we take the unhybridized electron from this carbon and from this carbon, and together they form a pi bond. It is a type of covalent bond that is coming out of unhybridized electrons. And why don't they go to the carbon? Because why don't they go to the hydrogen? Because hydrogen cannot have another electron. Okay, so of course it's not going to the hydrogen. So a double bond is 1 sigma, 1 pi. It's made out of two types of bonding. A sigma bond that comes from the hybridization, from these, and another one that is made out of the unhybridized electrons. So multiple bonds are, one of the bonds is sigma and the rest is pi. Okay, that means also that a triple bond will have 1 sigma and 2 pi. Why is that? Let's see. All right, we take a new piece of paper. A triple bond is sp hybridization. The carbon took 1 s and 1 p. This is the sp hybridization, and 2 of the electrons are in a hybridized. Okay, so carbon, carbon, this is a sigma, and this is a sigma. Now let me write it in red so that you can see the different sigma bond and sigma bond. Okay, also the other carbon, same thing. This is also sigma. Okay, so now each carbon has 2 electrons from the hybridization. They go to this bond, and 2 electrons that are not hybridized. So this is a not hybridized, this is a not hybridized, this is a not hybridized, and this is a not hybridized. This is this, this is this. Each comes with the 2 non-hybridized, and they form 2 pi bonds. This is 1 pi, and this is another pi. So triple bond is 1 sigma, 2 pi. And the 2 pi come from the non-hybridizing electrons. So this carbon has 2, this carbon has 2. So together we have 4 electrons, 2 pairs that form the 2 pi bonds. Capiche? So single bond, all sigma. Double bond, sigma plus 1 pi. Triple bond, sigma plus 2 pi. Single bond, sp3. Double, sp2. Triple, sp. This is what you need to remember. So far, so good? Now I have one question. Which bonds are more stable, sigma or pi? Okay, all right, on we move, on we move. So the pi bonds originate from the orbitals that are not participating in hybridization. All double bonds are made from 1 sigma, 1 pi. All triple bonds are made out of 1 sigma and 2 pi. On we move, on we move. You have here a summary. You have a summary. You see the number of groups around the carbon. sp3 means carbon has 4 partners. Bond angle 109.5 in a tetrahedral. sp2, 3 partners. sp, 2 partners. The angle and what kind of bonding. All right? And you see how bond strength and bond length are related. We discussed that many times. We won't focus on this again here. Okay? So, at your convenience, you have the type of bond, single, double, triple, length, and strength. This is helpful in homework and helpful to understand things. So this is just at your convenience. Okay? We move now to talk about 3 ways to draw heptane. Heptane is a molecule that has 7 carbons and 16 hydrogens. I can draw it like this, showing all the carbons and all the hydrogens. Do you know how much time it takes to do this? It's a lot of times and a lot of patience. And chemists don't have patience for this. Okay? So instead, chemists take the zigzag approach. Every point is a carbon. So this is 1 carbon, this is 2 carbon, this is 3, 4, 5, 6, 7. So the zigzag, every corner represents a carbon. And since this is all single bonds, you can draw the conclusion how many hydrogens you have. So the terminal ones, here we will have 1, 2, 3 hydrogens. Here we will have 2, here we will have 2, here we will have 2, here 2, here 2, and here 3. Do the math. 3 plus 3 is 6. 6 plus 10, 16 hydrogens. This is much easier to draw than this. Do you agree to that? So that is good to know. The zigzag method, I use the zigzag method a lot. So books as well, entrance exams as well, so get used to. And sometimes you have a mixture between the zigzag and the full construction. And what they do is they give you the end points, because here it is a CH3 and here also CH3. So this is a mixture between this and this. All right? It doesn't matter how you draw it, as long as you draw it correctly. Never carbon has more than 4 bonds. 1, 2, 3, 4. So far, so good? Perfect. You know what you guys deserved? Indeed. Let's take 10 minutes and come back at 11:36, and I will see you then. Now we move on to naming organic compounds. Okay, so just to remind you, counting carbons, met 1, et 2, prop 3, but 4, pent 5, hex 6, hept 7, oct 8, non 9, dec 10. So we need to be able to tell a person this is the name. And the good thing about naming organic compounds is when you hear the name, you know the structure. So first of all, you need to be able to say how many carbons the molecule contains. So met, et, prop, but, pent, hex, hept, oct, non, dec. You need to be able to count in chemistry. Okay? Counting carbons. That's the first step. So the good system is also allowing you to recognize what family the molecule belongs to. When we have the sp3, all sp3 molecules, the ending is "an", and we say that the molecule belongs to the alkane family. Alkane family. Alkane. And the ending "an" tells you it belongs to the alkane. So metan, meaning molecule, one carbon, all single bonds. Et-an means a molecule, two carbons, and belonging to the alkane family, sp3. Prop-an, molecule that has three carbons and belongs to the alkane family. Butan, pentan, hexan, heptan, octan, nonan, decan. So when you hear an, you know the molecule has only single bonds. This is the alkane family. When I have in the molecule a double bond, this family is called the alkane family. So all the members will end up with N. Eten, propen, buten, penten, hexen, hepten, octen, nonen, decan, or decen. So the ending N tells you there is a double bond there. Make sense? And the in ending belongs to the alkene family. Etin, propin, butin, pentin, hexin, heptin, octin, nonin, dekin, or decene. So in, you know there is a triple bond there in the molecule. Okay? Why don't I have methane and methene? Why don't I have that? So now all the way back. That's good. We have a repetition. Now it is time to talk about naming organic compounds. Thank you, Dustin, so much. Naming organic compounds. So first, what we need to know is we need to be able to count carbons. We need to, to count carbons. All right, how do we count? We count. 1 is met, 2 is et, 3 is prop, 4 is but, 5 is pent, hex, hept, oct, non, dec. 1, 2, 3, 4, 5 until 10 is met, et, prop, but, pent, hex, hept, oct, non, dec. So how do we apply this? All right. So we apply it like this. When we have a molecule that only has single bonds, this molecule belongs to the family of the alkane. So you use the ending an and say metan, etan, propan, butan, pentan, hexan, heptan, nonan, etc., etc. So you count 1, 2, 3, 4, 5 until 10, met, et, prop, but, blah, 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 and then you end up the ending an. When you hear the ending an, you know that this molecule belongs to the alkane family, sp3 carbons, no double bond, no triple bond, only single. When you have a double bond in the molecule, that molecule belongs to the family of the alkane, alkanes. So we have ethane, propane, butane, pentane, hexane, heptane, octane, nonen, decane, or decane, how you pronounce it. So the ending N tells you there is a double bond in the molecule. And there is there a chunk that has an sp2 hybridization, 2 carbons that have sp2. When you have a triple bond, alkene, that is the family of the alkene, we have methene, propene, butene, pentene, hexene, heptene, octene, nonene, etc., etc. So when we hear in, we have a triple bond and sp carbons. Not all of them, but at least 2. Okay, so alkan, only single bond. Alkane, we have there a double bond. Alkene, we have a triple bond. So metan, etan, propan, eten, propane, ethene, propene. Okay, so when we look at heptane, this is now this example, heptane is C7H16. It belongs to the family that has CnH2n plus 2, to the alkan family. Alkan, heptane. So, but there are more than just this heptane. There are branched molecules that have 7 carbons. Which one is which? So, as I said before, if you look at the molecule that is depicted in this slide, here we have 1, 2, 3, 4, 5, 6, 7. This compound also has 7 carbons, but it is not like the straight heptane. How do I discriminate? How do I know? And that is the whole thing about nomenclature in organic chemistry. You hear the name, you know how to draw the structure. So the straight chains are given here. Okay, pentane, hexane, heptane, octane, heptane, octane. These are straight chains. But what happens when they get branched? What happens when they get branched? So there was a group of smart scientists. They met and they decided on rules of naming. And these are called the nomenclature rules of IUPAC. IUPAC, International Union of Pure and Applied Chemistry. They have the rule, and the rules we will learn today. And when we finish, the minute we hear a molecule, we know how to draw it. The minute we hear the name, we know the structure. Okay, so here we have a straight pentane, and here we have 2-methylhexane. Where did they get the names from? Of course, first the rules. And what are the rules? The rules of IUPAC the rules are composed as follows. We have a prefix, we have a suffix, and a base. Okay, so you can compare it with our names, like John Erickson Jr., 3 pieces. So the prefix is telling me what branching do I have? What branching do I have? Because every branching looks different. The base is telling me how many carbons the longest chain has. And the suffix is telling me, is it an alkan, is it alkane, is it whatever family that the molecule belongs to. So we have 3 chunks to the name. And let's look at how it really goes. So every organic molecule has a name, and every name 3 parts. The first part, okay, is telling you the parent. Okay, it's telling you what is the longest straight chain that you have. The prefix is telling you the substituents, and the suffix is telling you is it alkan, alkane, alcohol, ketone, whatever. So you know immediately what functional groups there are in a molecule, how long it is, and how branched it is. So instead of reading this, let's go and see in the field what is going on, because this can be quite confusing. Okay, here we have these 2 molecules. What is the longest continuous carbon chain in the one here on the left? How can we count? We can count 1, 2, 3, 4, 5. This way we count 5. Or we can count 1, 2, 3, 4, 5, 6, 7, 8. 8. What is longer, 8 or 5? Of course, 8. So this molecule is considered to have a straight chain of 8 carbons. So 8 carbons is octane. Octane. So this is derivative of octane. Okay, but it is not a straight octane. There is something sticking out. Okay, we have here a branching with 1 carbon. Okay, branching with 1 carbon. What is 1 carbon? 1 carbon is met. Correct? So when it is a branching, I add il. Il tells me this is a branching. So I have met il. I have a branching with 1 carbon. So I have methyl octane. What is missing? What is missing? What is missing? If you look at this compound, what is missing? Let's draw it on a fresh piece of paper. Okay, that was not it. Let's draw it on a fresh piece of paper. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I counted. That the longest chain is 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is octane. Why is it octane and not octane or octene? Joshua, answer me, please. It's only single bonds. So this belongs to the family of the alkane. Okay, so I have a branching here that has 1 carbon. So it is met il branching. What is missing? If you look at the name, something is missing. No, all the hydrogens are there. What is missing? Joshua. The location of the methyl, exactly the location. because if the methyl is here, or if the methyl is here, it's a different molecule. So what is missing is the location of the branching. And we give the location also. We must give the location also. This is for methyl because it is on carbon number 4. 1, 2, 3, 4. But then you can say, really? Well, I don't want to count from right to left. I want to count from left to right. So this will be 1, 2, 3, 4, 5. So this would be 5 methyl octane. No, no, no. The rule says that you have to start counting from the side where the branching has the smallest number. So 4 is smaller than 5. You count from right to left. Capisce? These are the most important rules. There are more. Meet them as we continue. Okay, so back to the compound. All right, now we understand. Let me remove the mess I made so that you can see that marked here in yellow is 4-methyl octane. All righty. So what about the molecule here on the right? It doesn't matter if the straight line is drawn like this or bent. You look at the number of carbons in a row. So we count 1, 2, 3, 4, 5, 6, 7, 8, because counting this way doesn't matter how you put it on paper. Okay, on paper is not really how the molecule looks like. All right, so you don't you don't count 1, 2, 3, 4, 5, 6, 7, because then you will have 7 in a row, which is smaller than 1, 2, 3, 4, 5, 6, 7, 8 in a row. So don't let the fact that it is drawn like this confuse you and say, yeah, but the straight line is like this. Yeah, the straight line is like this. You have also the carbons in the row in this way, but you have carbons in the row also in the other way. And that is what matters. If you count the longest continuous chain, the longest continuous chain, that is the parent molecule. Okay, so clearly now this one that I'm now pointing at is also an alkane, because it doesn't have any triple or double bond. And I count 1, 2, 3, 4, 5, 6, 7, 8. Meaning that at carbon 4, I have a branching of 2 carbons. Okay, and 2 carbons, 2 means et, add il to it, methyl et il. So every branching ends up with the il, so the branching here will be et til. So this molecule will be 4-ethyl octane. Why octane? Because the longest continuous chain is 8 long. So octane, and the branching is at position 4 and has 2 carbons to it. So that is ethyl. Okay, so we count also in this case from right to left. We don't count from left to right, because if we did 1, 2, 3, 4, 5, the branching will be at carbon 5. Okay? So let's see another way to which we represent a longest chain. Okay, so longest chain can also be drawn like this. Don't confuse and look at only at this one. Don't, because this is not the longest chain. The longest chain is 1, 2, 3, 4, 5, 6, 7, 8. And here the branching is 3 carbons, so it is prop-il. So this will be 4 propyl octane. Okay, make sense? So when you stick to these rules of first finding the longest chain, then looking at the branching and giving the branching the smallest possible number, okay, then you will write everything perfect. Okay, so we will practice a little bit more. Let's look at the molecules in slide 29. What is the longest chain here? What is the longest chain here? If I go this way, it will be 4. If I go this way, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is pentane. What about this here? 1, 2, 3, 4, 5, 6. This is hexane. Now you can ask me, hey, but if I count 1, 2, 3, 4, 5, 6, it is, how do I count? This way or this way? Well, it doesn't make a difference in this case. Why? Look at that. Let's consider 1, 2, 3, 4, 5, 6. Then I have 2-methylhexane. 2-methylhexane. All right, so counting this way, 1, 2, 3, 4, 5, 6, 2-methylhexane. If I count this way, 1, 2, 3, 4, 5, 6, I also have 2-methylhexane. So it doesn't really matter. Okay, what about this guy here? What is the longest chain? 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. Or 1, 2, 3, 4, 5, 6. So the longest chain is 6. This is also hexane. Okay, so if this is hexane, what kind of hexane is it? What kind of hexane is it? Where do I start counting? 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5, 6. Let's look. So now I understand that this is an hexane, correct? Is it so far so good? Okay, let's say that we start counting from here. 1, 2, 3, 4, 5, 6. Then I have one branching at position 3. And the other branching is at position 4. So this is this branching at position 3. And this branching at position 4. If I count the opposite way, 1, 2, 3, 4, 5, 6, I also have branching at position 3 and branching at position 4. So in this case, it doesn't matter if you count this way or that way. It gives you the same name. Okay. So note that it does not matter if the chain is straight or bendly drawn. If it is drawn like this or drawn like this or drawn like this, find the longest chain, continuous chain. So this is a warning that they will try to confuse you by drawing the chains in a different way. Capiche? Don't fall into the trick. Okay, so when you look at a molecule, you first count the longest chain. Then you look at the branching, what branching you have. And then you look where the branching is. But what happens if you have something like this? Okay. You have a molecule 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So clearly this is an octane. And I count this way. 1, 2, 3, 4, 5, 6, 7, 8. So this is clearly an octane. So far, so good? Okay, now let's see the branching. I have one methyl, is this, and I have one ethyl. So how do I count? Do I count 1, 2, 3, 4, 5, 6, 7, 8? Or do I count? Let's take, what color do we take now? What color do we take now? Should we take brown? It's an ugly color, but well. Let's take brown. So do I count this way or do I count this way? 1, 2, 3, 4, 5, 6. So are the two branching at 4 and 6 or at 3 and 5? So it will be at 3 and 5 because if you add these two numbers together, they will give you 8. And if you add these two numbers together, it will give you 10. And the first branching in this name, the branching gets the smallest number. And 3 is smaller than 4. So far, so good? So this will be 5 ethyl, 3 methyl octane, and not 4 ethyl, 6 methyl octane. Okay? All right. So now the question is, why did I put the 5 ethyl before the 3 methyl? Why did I do that? Why didn't I give the name 3 methyl, 5 ethyl? Okay, so let's remove the wrong name so you won't be confused. Let's remove this. So why did I give the name 5 ethyl 3 methyl and not 3 methyl 5 ethyl? Why? It's more logical that the small number will be before. But why did I do that? Okay, Dastan, you have an idea? No. Good try, very good try, but no. It is because the rule says that the branching with the letter before in the alphabet will be first. So E is in the alphabet before M because we have A, B, C, D, E, F, G. So E is before M. That's why E is presented. Ethyl is before methyl. Complex, huh? So these are the rules. So here we have a nice summary of some of the branching: methyl, ethyl, propyl, butyl, pentyl. The il tells you this is a branching. This is a substituent. Okay, and you have, again, methyl, ethyl, propyl. You have possibility to have branched propyl, so that the chain is here, and you have the propyl like this. You see the difference? Let me draw the difference. This can be a branched propyl. Okay, this is the chain, and this is the branching. But you can also have the branching like this. See, like that. So this is also branching with 3, and this is also branching with 3. But this is branching that is straight, and this is branching that is branched. So you see, organic chemistry is very complex. Even the branching can be branched. Okay, and that's what it says here. You can have 3 carbons that are straight, like here. So the chain would be here. But you can have the chain also creating a branched branching. So methyl, ethyl, propyl, isopropyl, N-butyl. Okay, so it's maybe not so necessary immediately to look at this. Okay, but when you have a ring branched, we call it phenyl. That is something that we will learn. Don't worry about it right now. This is good for the homework to have a look. But when we're done with organic chemistry, you will know that this is a phenyl substituent, or this is an ethyl methyl propyl. In the meantime, when you do the homework, use the PowerPoint. If you don't know what the branching is called, just look here. Okay? But as you practice, you would master it. And that is the reason, of course, that you must practice. Otherwise, you won't be able to name the molecules. Okay? So, again, how do we call this molecule? We have 1, 2, 3. No. 1, 2, 3, 4, 5. No. 1, 2, 3, 4, 5, 6. This is hexane. Capiche? And why is it hexane? Because we do not have a double bond. Goody. Now, how do we count? Left to right or right to left? Let's see. 1, 2, 3, 4, 5, 6. If I count this way, from right to left, this methyl will get number 2. If I count the other way, the methyl will get number 3. So we do not count from left to right, we count from right to left. Okay, because you can see the difference. This would be 2 and 4. And if I count the other way around, it will be 3 and 5. Capiche? Okay, so how do I call such a molecule? How do I call such a molecule? I have 2 methyls sticking out. So this is a hexane and it has 2 methyls. The 2 methyls are at position 2 and position 4. So the name would be 2,4-dimethyl hexane. Why dimethyl? What does the word D tells you? 2. So the name tells you I have a hexane, and at position 2 and at position 4 I have 2 methyls. You hear that? This is in fact instructions how to draw the molecules. Can you see that? That these are instructions to write the molecules. Take hexane and at position 2 and at position 4 stick 2 methyls. 2,4-dimethylhexane. All right? And of course, you count from the side, you start counting from the side, which gives the substituents the smallest number. Okay, what about this monstrosity? Would you like to try to do this monstrosity by yourself? Would you like to give it a try? Go for it. The real name is 5-ethyl 2,5-dimethylheptane. Oopsie, where does this come from? Any way you count, it is a heptane. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So this is heptane. Is it so far so good? Heptane. Why is it heptane and not heptane? It is because we don't have a double bond. We don't have a triple bond. This is an alkane. Okay, so now the question is, where do I start counting? Do I count from left to right or from left to right or from right to left? Okay, let's see. If I have 1, 2, 3, 4, 5, 6, 7, then the first substituents get the smallest number this way. Correct? Because if I start counting from the other direction, then the substituents will start at position 3. 1, 2, 3. So I count 1, 2, 3, 4, 5, 6, 7. So I have methyl at position 2 and methyl at position 5. I also have at position 5 an ethyl. So always E before M. E before M. Doesn't matter that you have a D. It doesn't matter, the methyl. So this will be 5-ethyl, because at position 5 I have an ethyl, and then it will be 2,5-dimethylheptane. And between numbers and letters, I have a stripe, and between two numbers, I have a comma. So, comma between the numbers, otherwise it would look like 25. So, yes, that is wrong. That is wrong. Okay? Any more questions? 5-ethyl 2,5-dimethylheptane. That is the name. What if the main branch is 3-part? What do you mean? What if the main branch is 3-part? If the main branch... Sure? Joshua, here is the pen. Tell me what you mean. If the branching has 3 carbons, okay, so the question is, if I understand you correctly, what? All right, so let's continue. Don't forget that when you list the substituents, you list the substituents in alphabetic order. Okay? You ignore the D3 tetrasec, the number that tells you is it dimethyl or is it trimethyl or is it tetramethyl. You ignore that. It is still a methyl. Okay? All right, let's do some practice because then we will understand what is going on. What happens if in both directions the same lowest number? So if you have 1, 2, 3, 4, 5, okay, this is pentan. Here the branching starts at position 2, if I count this way. And if I count this way, I also have a branching starting at position 2. Correct? So what do I do? Do I count from left to right or do I count from right to left? Okay, let's see what do I get. Let's say that I start counting from right to left. Then I have position 2, 3, and 4. That would be 2, 4, 4, because here I have branching at position 4. So it would be 2, 4, 4, 3 methyl pentan. 2, 4, 4 is if I count this way. Okay, 2, 3, 4. But what happens if I count the opposite direction from left to right? Then I will have 2. This will be carbon 2, and this will be carbon 4. Then I will have 2, 2, 4, 3 methyl pentan. Add up this 2, 2, 4, smaller number than 2, 4, 4. Okay, you see that this 2 is smaller than this 4. 2 is smaller than 4. This is the right name. So it is not 2, 4, 4, 3 methyl, but it is 2, 2, 4, 3 methyl. Because you look at the combination. So far, so good? So that is in the case where you have both, whether you count from left to right or from right to left, the smallest number is 2. So you go and look at the rest of the molecule. Okay, what about this example here? What is this? 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. No, 1, 2, 3, 4, 5, 6, 7. This is clearly octan. Okay, is it clear that this is octan? Because the longest continuous chain is octan, is 8. There is no double bond, so it is not octane or octene. So how do I count? How do I count? Do I count right to left or left to right? That is the good question. So now let's see. 1, 2, 3. This is position 3. 4, 5, 6. So this is when I count this way. Okay. So what if I count the other way around? I will have 1, 2, 3, 4, 5, 6. So I have the difference between 3, 5, 6 and 3, 4, 6. Okay, 3, 4, 6 is smaller than 3, 5, 6. So the name would be 6-ethyl 3,2-dimethyl octan. And not the opposite, and not 3-ethyl 5,6-dimethyl octan. It is because 4 is smaller than 5. Does this make sense? Okay, all right. So what if you have the same number of substituents? So let's look at these two cases. I have 1, 2, 3, 4. This is clearly a butan. It is chlorine and bromine. So if I start this way, it will be 1, 2, 3. I have a branching at position 2 and a branching at position 3. And if I count the other way around, I have the same, branching at 2 and branching at 3. So what is this? Is it 2 bromo, 3 chloro, or 2 chloro, 3 bromo? Well, then the alphabet decides again. The alphabet decides again. So we have 3 bromo, 2 chloro. The substituents are listed alphabetically. B before C. Bromo, okay? Bromo before chloro. So 2 bromo, so we start counting this way so that Br will get this smallest number. So 2 bromo, 3 chloro, and not 3 bromo, 2 chloro. Again, if you look at this molecule here, it has 4 carbons, 1, 2, 3, 4. If I count from right to left, then the substituent starts at 2 and the second one at 3. The same thing will happen if I will count from left to right. The first substituent at 2 and the second at 3. So what is this? What is this? Then you always give the smallest number to the one that is closest in the alphabet. So it will be 2 bromo, 3 chloro, and not 3 bromo, 2 chloro. Because then the B will get the bigger number, and this is not correct. Okay? Is this clear? Let's look at another example. 1, 2, 3, 4, 5, 6, 7. This is heptan. This is heptan. How do I count? Right to left or left to right? Let's see. When I count the red way, okay, I have 1, 2, 3, 4, 5. When I count the green way, this way, I count 1, 2, 3, 4, 5. It's the same. Which is considered the right name? E-ethyl gets the smallest number. So 3-ethyl, 5-methyl. This is a very special case, just like this. And if you have the same numbers, whether you count from left to right or from right to left, then the alphabet decides. Just like Br got the smallest number here, 2 bromo. Also here, ethyl will get the smallest number, 3-ethyl, and not 5-ethyl. So this is another rule. There's a lot of rules, huh? And the last rule. What happens, and this is a bit of an overkurs. Do you know what it means, overkurs? Okay, so if you have a compound that has 2 or more chain with the same length, which one do you choose? So let's look. 1, 2, 3, 4, 5, 6, 7. This is one way to count. But I can also count 1, 2, 3, 4, 5, 6, 7. Which one do I take? Do I take the red one or do I take the green one? Because this is heptan and this is heptan. Which one do I go? Which way do I go? Which way do I go, the red or the green? Now they tell you, you select the one that has the greatest number of substituents. So let's see. If I count this chain, if I take this chain, I have 1 substituent, 2 substituent, 3 substituents, 4 substituents. Okay, what happens if I do the other one? Let's remove. What happens if I decide to go with this guy here? Okay, then how many substituents I have? I have 1, 2, and 3. So I take the chain that gives me the most splitting, the most substituents, and this is when I count this way. Then I have 1, 2, 3, 4 substituents. Okay, that's it. These are the rules, and that is more than enough because that is confusing, don't you think? But once you get used to it, it will be no problem. So the only thing is to practice. Let's practice. Let's practice. Please give me the name of this molecule. And remind me, please, to turn on the recording. Thank you, Dustin. I owe you. I didn't turn on the recording. So the name of this molecule is 1, 2, 3, 4, 5. 5 is pentan. Splitting substituted carbon 3, 3-methyl pentan. 3-methyl pentan. And it is pentan because it has no double bond. Okay, so you see the name here, 3-methyl pentan. Okay, so now we're doing the second one. So this would be number 2 is 1, 2, 3, 4, 5, 6, 7. It is heptan. We have 2, 4, 5. The branching, it is position 2, 4, and 5. This would be 2, 4, 5, 3-methyl heptan. Did you get it? Well done. And you see, here is 2, 4, 5, 3-methyl heptan. Okay. All right. Let's take the next one. This group here is called isopropyl. So the letter I. Okay. Letter I is for you. I before M. So what would be the name of this molecule? So again, we have heptan. 1, 2, 3, 4, 5, 6, 7. 7 carbons. We start counting from right to left because then we have the substituents getting position 2. And that is 2, 3, 4. The isopropyl is at position 4, I before M. Isopropyl, E before I before M. I have 4 isopropyl, 2 dimethyl heptan. Dimethyl heptan. And this guy here, homework. And you will get a lot of practice. You see, this is also homework. You have the names and you have the summary of all the UPAC names of alkan. So all the rules in one slide, you have it. The first rule, find the longest chain. The second rule, the substituent, get the smallest possible number. If you have two substituents, alphabetically, ethyl before methyl. Okay? If both sides have the same lowest number of the substituents, choose the side that has the smallest combination. That the next substituent, look at the next substituent and make sure it gets the smallest number. Okay? If you have the same molecule, like I showed you, bromo and chloro, the one that gets the smallest number is alphabetically, the B before the C. And if you have two chains, which one would you choose? You choose the one with the biggest number of substituents. So here you have the summary of all the UPAC rules of nomenclature. Okay? All right, so we talked about straight lines, straight chains, and we talked about branching, but we can also have rings. Rings is something like this. It is a closed structure. You see, there is no open chain. When we look and we see something like this, we add the prefix cyclo. So I look at the chain, I see there are no double bonds. This is an alkan, but because it is in a ring, I call this cycloalkan. So cyclohexane, cyclopentan, cyclobutan, cyclopropan. I count the number of carbons, 1, 2, 3. This is propan, cyclopropan. 1, 2, 3, 4, butan, cyclobutan. 1, 2, 3, 4, 5, cyclopentan. 1, 2, 3, 4, 5, 6, cyclohexane. And I can draw it like this if I have patience and time, which I don't. This is how we draw cyclohexane. 1, 2, 3, 4, 5, 6. This is how we draw cyclopentan. 1, 2, 3, 4, 5. This is how we draw cyclobutan. 1, 2, 3, 4, etc., etc. So when I have a ring, I add cyclo. Capish? Cyclo. So when you have a structure that is closed, it is a cyclo. So what if I have a cyclo with a branching? So what do I have here? I have methyl and an ethyl. So I need to stick to the same rules. So this is not an unbranched ring, it is a branched ring. So how do I name a branched ring? Okay, let's have a look. Let's have a look. How do I name a branched ring? So when I have one branching, this is methyl cyclohexane. And it doesn't matter if I draw it like this, or I draw it like this, or I draw it like this, or I draw it like this. It's the same molecule. I just turn it and it's the same molecule. Can you see that this is the same as this, is the same as this, is the same as this? Is you just turn it. Okay? So this would be methyl cyclohexane. But what if I have two methyls? Then things get complicated. By the way, how is the head? How? Head is good? Not exploding yet? Still working? Praise be the Lord. Patience, your head? Still working? Great. Okay, because this is not simple, to say the least. Okay, so what if you have 2 methyl stuck on the ring? So do I say 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6? Do I count clockwise or counterclockwise? In this specific case, I stick to the rules to give the substituent the smallest, lowest possible number. So this would be 1,3-dimethyl cyclohexane. 1,3-dimethyl cyclohexane. Capiche? And not 1,5-dimethyl cyclohexane. So I number in this case clockwise. I don't always do clockwise. I always have to look at the smallest possible combination. So far, so good? Okay, all right. So what if I have the following? What if the ring has a chain stuck to it, and what is this? Is this a chain substituted with a ring, or a ring substituted with a chain? What would it be? You count how many carbons you have. The chain has 4, the ring has 6, the ring overrules. More carbon in the ring overrules, and this will be butan or butyl cyclohexane. Because 1, 2, 3, 4, the substitution is 4 carbon long. This is butyl cyclohexane. Okay? And not cyclohexyl butan. So the chain, because it is smaller, that is the substituent, not the ring. Okay, is it so far so good? So the parent molecule is the cyclohexane. But what happens if you have more carbons in the chain? Then the opposite is correct. Then the chain overrules, and you have cyclobutyl hexane. 1, 2, 3, 4, 5, 6, 6 carbons. This is hexane. The smallest number for the substituent is number 1. This is, we count from left to right. This would be 1 cyclobutyl hexane. So you see who is bigger, and who is bigger is the boss. Okay, so you see the difference, whether you have more carbons in the chain or more carbons in the ring. So far, so good? And molecules in organic chemistry get so super complicated, they will not ask you the complicated things in entrance exam. They will not, because that takes long time to sit and figure out and to start counting, and average you have about 2 to 3 minutes per question. So you, as in the same way that you don't get very complicated balancing of equations, you won't get complicated names. Okay? Is it so far so good? So cycloalkanes, we have cyclopropan, and here we have methyl cyclohexane. And this is another good example. Here we have a ring, and the ring has 2 branching. Okay, so who is getting number 1 and who is getting number 2? Do I go 1, 2, or do I go 1, 2? Ethyl is E, methyl is M, ethyl gets number 1. So this will be 1 ethyl, 2 methyl cyclohexane, because E before M. So we give number 1 to the ethyl. Okay, here you have some practice for homework. Count the number of carbons, and the question mark, ignore the question marks here, okay? Ignore that. There is a reason why there is a question mark there. And why there is a question mark, we're going to see next week. Why I drew these molecules in a special chemistry software. And when the software saw this, he said, hey, you forgot something. What kind of carbon is this? Is it what it is? Why there is a question mark here? All will be revealed next week. So far, so good? So this is homework, and you have the answer. Are you ready to go to the alkanes and the alkenes? Are you ready, or do you need a little break? No, you don't need a little break. What about Joshua and Patience? Can you absorb more without a break? Okay, what about Joshua? Are you still okay? All right, so now we move to those molecules that have double bond and triple bond, alkanes and alkenes. Just to remind you, when we have the straight chains, ethane, propane, butane, pentane, blah, 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 or ethene, propene, butene, pentene, etc., etc. So naming alkanes according to EUPAC. Okay. See if this was not complicated enough. Now comes an additional complication. All right. So when we look at these two molecules, they look exactly the same except for one difference. One has a double bond here and the other one doesn't. One is an alkane and the other one is an alkane. So do we name them the same? Let's look. What is the longest chain here? 1, 2, 3, 4, 6, 7, 8, 9. Let's count, see what happens here. 1, 2, 3, 4, 5, 6, 7, 8. So this is 9 carbons. Okay? So this is, in fact, none. But is it the same rule when we have a double bond? And the answer is no. No. When we have a double bond, we count the longest chain that includes the double bond. Okay? So if we count this way, we don't include the double bond in the longest chain. Correct? So we count this way. We must include the double bond. Is it so far so good? So on the right, the molecule will be 1, 2, 3, 4, 5, 6, 7, 8. It will be 8 long and not 9 long. 8. So let's have a look. All right. Always look at the longest chain. The longest chain, if you see that there is a double bond in the molecule, the longest chain has to include the double bond. As you see here. must include the double bond. All right, perfect. So the longest chain of the alkane must include the double bond, the pi bond. So, well, how do we count? How do we count? Do we count 1, 2, 3, 4, 5, 6, 7, 8? Or do we count 1, 2, 3, 4, 5, 6, 7, 8? Okay, here is the second rule. The CC bond, the double bond, must get the lowest possible number. So if I count from left to right, the double bond will get position 7 and 8. If I count this way, it will get position 1 and 2, and this is the correct one. So the pi bond receives the lowest location, even if it competes with the alkyl group. So this is 1, 2, 3, 4, 5, counting this way and not this way. Are there any questions? That's the rule. There's nothing we can do. Okay. So after I found the longest chain and I gave the pi bond, I gave the pi bond the smallest possible combination. Okay, what do I do then? I look at what substituents that I have. Okay, so on the left you have an alkan, and on the right you have an alkane. On the left, this is the biggest chain, and we have two substituents, methyl and ethyl. And I count from left to right to give the first substituent the smallest number. So this will be carbon 2, this will be carbon 6. What about the alkane? Alkane, this is the longest chain, okay? And now the question is, what do I do next? What do I do next? Of course, because I count this as carbon number 1 and this carbon number 2, this would be carbon number 3. And per definition, this will be carbon number 7. Because I already know where to start counting. The double bond decides. 1, 2, 3, 4, 5, 6, 7, 8. Does this make sense? All right. So how do I call this compound? This would be, this is a propyl, P. This is a methyl, M. What is in the alphabet before? The M or the P? A, B, C, D, E. The M. So this will be 7-methyl, 3-propyl, and now it was in the past, it was 7-methyl, 3-propyl, 1-octane. Why 1-octane? Because the double bond starts at carbon number 1. So that's what the molecule tells you, 7-methyl. Now I'm making such a mess. I don't know if you can see it. All right, I will remove all the ugly red things and take a brown color. All right, so 7-methyl, 3-propyl, M before P, 1-octane. Why 1-octane? You also need to give the location of the double bond, not only the location of the substituents, but also where the double bond starts. And double bond starts at carbon number 1. Okay, so this is the name. 7-methyl-3-propyl 1-octane. But, and what is the but? There is a synonym. There is a synonym. And what is the synonym? You can also call it 7-methyl-3-propyl oct 1N. So instead of 1-octane, you say oct 1N. It is an octane with the N and the double bond at position 1. Why? Synonyms. So either is correct. Either is correct. So you have the 7-methyl-3-propyl oct 1N. N is a double bond. N is the same as double bond. So 7-methyl-3-propyl and the octane has the double bond at position 1. Or you can call it 7-methyl-3-propyl 1-octane. Either is correct. Okay? All right. So both allowed. 3-pentane is the same as pent-3N. 2-butane is the same as but-2N. You see, you split. And N means a double bond. Yep. That's the rule. When you have a ring, and in the ring we have a double bond, the same is valid. This is cyclohexane. This is cyclohexane. Okay, you switch the an for n. So cyclohexane, cyclohexane. Cyclobutane, cyclobutane. Cyclopropane, cyclopropane. Cycloheptane, cycloheptane. Capiche? But you have to add, when it is a ring, you must add a cyclo. Otherwise, the person doesn't know it is a ring. All right. Okay. And what happens if you have a substituted ring? So we have here methylcyclohexane. But what happens if I have a cyclohexane and a methyl stuck to it? Of course, the double bond get position 1. So 1, 2, you include the whole double bond. You don't go this way, you go this way. Okay, because you include all the carbons of the double bond. So 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5, or 1, 2, 3. No, you don't do that. You don't do that. You go this way. And you see that there is a mistake here. Okay, and what is the mistake here? You don't count 1, 2. You count the other way around. Okay, you count the other way around. If you start like this, you also include the whole double bond. Correct? Exactly. So let's look at the new piece of paper and I will explain. If you have here a double bond with a methyl, you must include the double bond. Double bond must be included and get the smallest number. Okay, so I can count 1, 2, in which case 3, 4, 5. So the methyl will get 5. But I can also count 1, 2, that also includes the whole double bond, 3, 4. Correct? I can count counterclockwise and I can count clockwise. But if you count clockwise, your methyl will get position number 5. And 4 is smaller than 5. So you count 1, 2, 3, 4. This is 4-methyl cyclohexane. Okay? 4-methyl cyclohexane, or the synonym methyl cyclohex 1N. So you can choose how to call it. So if you go this way, it is wrong. If you go this way, it is right, because 4-methyl beats 5-methyl. Make sense? So always, always you must include the double bond, and you see that this is a mistake. You don't count like this. You count 1, 2, 3, 4, just like that. Are there any questions? So you see all the time the same principle is coming over and over again. The substituent, the smallest number. Substituent, the smallest number. And if you can count from left to right or right to left or counterclockwise or clockwise, the rule is look at the smallest number. So far, so good? Okay, all right, great. So here you have some more homework. A bit out of space, but you have a double bond. You have ignored as I said, ignore the question marks, because I needed to add something that would complete the name, but that is the topic of next week. Okay, so you have here a molecule that is branched with a double bond. Try to understand why it is called oct-2N, 1, 2. Always the longest chain must include the double bond. All right, more examples and more examples and more examples and more examples and the answers to that examples. This is homework to practice the naming. And if you don't practice, guys, you're going to be completely confused because you got so many rules today. Capiche? Okay, there's another thing I want to say. There's another thing that I want to say. All right, here you have molecules that have more than one double bond. Okay, no, not this one, but anyway, this one and this one and this one. Okay, one double bond is 1N. Okay, if you have two double bonds, what do we call them? A molecule that has two double bonds. Exactly, it is DN. And a molecule that has three double bonds is called a 3N. Okay, so note, this is for now a little bit over, but you can do it. So just look, you have 1, 2, 3, 4, 5, 6. It is 6 carbons with two double bonds. How do I start? Do I start 1, 2, 3, 4, 5, 6, or the opposite? So if I start counting, like this, 1, 2, 3, 4, you see that this double bond here starts at position 2, and this double bond starts at position 4. Okay, and what happens if I count the other way around? 1, 2, 3, 4. So it doesn't matter. It is 2,4-hexadiene. Okay? So always the smallest number. So this is a little bit over course, but try to see if you figure it out. I mean, it's good to give you sometimes a little bit more than you need, because if you figure this out, you can definitely deal with the others, right? But it is my duty to tell you that this is a little bit too much. So far, so good? All right. What about the alkenes? That's the last part of the lecture today. The alkenes. The alkenes. Alkenes have a triple bond. So, remember the alkane? We had it when we talked about the alkane. We do the same thing. Compare alkane with alkene. Here we don't have any multiple bond. Here we have a triple bond. So the longest chain always in an alkene, just like an alkane, always contains the triple bond. So you don't count this way, you count this way. Make sense? So you see things start coming over and over and over again. Okay? And you identify the substituents. Also here we have a methyl and a propyl. Okay? And also here, the triple bond gets the lowest possible locant. So we have the triple bond starting at position 1, and we count this way. All right, is it so far so good? Just like an alkane, no difference there. Okay, and also here we have synonym. So this molecule will be 7-methyl, 3-propyl, 1-octene, 1-octene, and the synonym is 7-methyl, 3-propyl, oct, 1-ene. This is a synonym. In means triple bond. And you see, example, all right? You have a molecule that contains a triple bond. This is alkene family. Alkenes. Okay, so as you can see, we are talking about the alkenes. Triple bond, alkene. Double bond, alkane. No multiple bond altogether, only single will be alkane. So alkane, no double bond, no triple bond. Alkane, double bond. Alkene, triple bond. Is it so far so good? And also here you have a synonym, 7-methyl, 3-propyl, 1-octene, because it is octene, and the double bond starts at position 1. But you can also have the synonym 7-methyl, 3-propyl, 1-ene. So what is this molecule? What is this molecule? Let's see what is the longest chain that contains the triple bond. 1, 2, 3, 4, 5, 6, 7. Okay, where does the triple bond start? Is it carbon 3 or is it 1, 2, 3, 4? So, of course, it starts at carbon 3. So this is actually 3-heptene. And then the rest of the substituents we do the same as we always do. So if this is carbon 1, okay, and this is carbon 2, and this is 3, and this is 4, and this is 5, and this is 6, and this is 7. Just like here, that's the same thing. I just drew it differently. 1, 2, 3, 4, 5, 6, 7. Then I have the substitution of the methyl at carbon 2 and at carbon 6. So this will be 2,6-dimethyl, 2,6-dimethyl-3-heptene, or hept-3-ene. Okay? All right. Practice. 1, 2, 3, 4, 5. And you have the numbers here. This will be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have the substitution at position 3 and at position 4. This will be 3,4-dimethyl-1-pentene. Why? Because the longest chain that includes the triple bond has 5 carbons. 1, 2, 3, 4, 5. Capiche? Okay, so now we've done a lot of practice already. The rest will be homework. Try to figure it out, and don't forget that if you're stuck, you can always call. Call by email, not by telephone. I don't answer telephone. So again, the synonym 3-heptene is the same as hept-3-ene. 2-butene is the same as but-2-ene. And the same thing holds for the alkanes. 3-heptane is the same as hept-3-ene. 2-butane is the same as but-2-ene. You see the similarities? N means one double bond. Ene means one triple bond. Okay, all right. So what happens if a double bond meets a triple bond? What happens? Okay. Who rules? Who overrules? Okay. So when I have a molecule that has both a double bond and a triple bond, I call this an N-ene molecule. N-ene, it has a double bond and a triple bond. Okay, so let's see, how do I count? So let's look at this molecule. It has a triple bond and a double bond. So the first multiple bond is at position 1. So I look at where is the multiple bond, and here the multiple bond doesn't matter that it is a triple bond, it starts at position 1. If I count this way, the multiple bond will start at position 2. So let's count. 1, 2, 3, 4, 5, 6. This is 6 carbons, and it would be hex 4n 1-ene. Why the n before? Why did I not call it 1-ene 4n? Because E is before Y. E and Y. Hex 4n 1-ene. Okay, so far so good. So this is also a bit of an over. Okay, and you have some more examples, some more examples. What happens when I have something like this? Okay, the multiple bond starts at position 1. 1, 2, 3, 4. This will be hex, 1N, 4In. Alrighty. So, fine. Now I know. But what happens if in the molecule I have functional groups like this and like this, and sulfur, for example? These are called functional groups because they have other bonds other than just CH and CC single bonds. So it is derivatives of hydrocarbons. Derivative of hydrocarbons are defined as having carbon and hydrogen bonds. But here we have oxygen, sulfur, nitrogen. These are called this and this and this, and these are called functional groups. Functional groups. They're derivatives of hydrocarbons with different groups on them. You see OH, COOH, sulfur, nitrogen. So the names of such molecules we will discuss every time we talk about a functional group. So when we talk about aldehydes and ketones, we will talk about the names then. When we talk about amines, we talk about the naming then. That's why it is so important that you will practice the names now, because it's all built one on another. Okay? And you see also that some functional groups are more valued than the other, that carboxylic acids have the highest priority compared to ethers. So if you have in a molecule both a carboxylic acid and an ether, then this is a carboxylic acid. The name is carboxylic acid. The carboxylic acid has the highest priority. So that is the reason when you have an amino group and an acid, this is an amino acid. It is an acid with a nitrogen and not an amine with a carboxyl. So we will talk all about this priority list in the near future. But it just shows you that you need to practice the names now because it's going to get more complex. We're going to talk about alcohols. We're going to talk about ketones, aldehyde, nitriles, amide, esters, anhydrides, the whole shebang of organic chemistry. Okay? So what are functional groups? A group of atoms that when added to the hydrocarbon changes completely the properties. The properties, all of the properties, the physical properties, the chemical properties, everything. And you saw that there is a whole list of functional groups, and we're going to talk about all of them in the near future. Okay? So this is just an in. This is overkurs. If you want, you can read this, but it is not really a must. Okay? So compound that has two types of bonds, triple bond and a double bond, is called an N-in molecule. And you see how we name them. We know that this is a little bit, a tiny bit overkurs, but at the end of the organic chemistry, we'll get back to these. So for the time being, I recommend to look at this, but if you think that your head is full, then just focus on all the other molecules and not just the N-ene. Okay? Look at the alkanes that we learned. Look at the cycloalkanes. Look at the alkanes and the cycloalkanes. Look at the alkenes and all the rules. And if you want, look at the N-ene. That will come a little bit later, but not right now. Okay? All right. And here is a little practice in case you want to have a check on the overkush. If you want to practice the overkush, you are allowed. You have to look at these molecules and try to figure out why the name is the way that it is written here. Okay? With slide number 84, we came to the end of the lecture today. Are there any questions? I would like to wish you all the very best and thank you for attending. The next lecture is going to be practice. Goodbye. Take care.